Yeah, so welcome to the fourth lecture of this class on model predictive control and reinforcement learning. And today I want to introduce a technology that is at the core, let's say, at the intersection of the two fields. So it's relevant for both MPC and for RL. And this technology is called dynamic programming. And I mentioned already yesterday that this all goes back to a famous mathematician, actually. This mathematician was called Bellman, Richard Bellman, and he wrote in particular this beautiful book from 1957 about dynamic programming, which popularized the method and is extremely rich and contains many of the ideas on which we are building nowadays. The language slightly evolved over the years, and that's also due to the fact that the field of reinforcement learning started somehow with a different language, and things have only later been unified. And I think one of the great unifiers in this respect between reinforcement learning and dynamic programming is Dimitri Bertsekas, who wrote wonderful textbooks. I also want to recommend these books maybe directly now. In particular, this one that's called Reinforcement Learning and Optimal Control, I think is a good book. And also the classic Optimal Control, Dynamic Programming and Optimal Control book. I also like that a lot. Beautiful books, a great writer. So what we do here is we give an MPC-centered perspective on dynamic programming. And I want to basically introduce it with a few examples. And then we in particular detail the linear quadratic regulator, which is a technology known to every control engineer and very widely used in daily life control for control of linear systems that need to be stabilized around set points. And it's basically based on dynamic programming. That's why I decided to put it into the same lecture. So the lecture will be divided into 5 parts. And after each part, as usual, we do a little break for discussion. We first start with dynamic programming on finite horizons, then go into this LQR, linear quadratic problems, venture into infinite horizon problems, which are really at the end what we want to address in this course. Here we think usually of infinite time evolutions. A few comments or generalizations on stochastic and robust dynamic programming, which are pretty easy once you're in this dynamic programming framework. Surprisingly easy, I should say, for someone who comes like I from the field of MPC. Where stochastic and robust is, let's say, orders of magnitude more difficult than the deterministic case. And last, I want to conclude with some remarks on monotonicity and convexity preservation properties in dynamic programming, which I think we should know about and which are not so popular. Some, in particular, the convexity notion isn't covered, I think, in most textbooks. So let's start with the basic idea. And it's all based on an observation that Bellman called the principle of optimality. That's the name he gave to it. And here are his own words. And he says, an optimal policy has the property that whatever the initial state and initial decision are, the remaining decisions must constitute an optimal policy with regard to the state resulting from the first decision. Sounds trivial, right? Yeah. But it's, and it's obvious, maybe you could say. Why is it obvious? Maybe let's try to think of it logically, right? So if the remaining decisions wouldn't constitute an optimal policy, then the whole thing wouldn't be optimal, right? Yeah, you can see it from different perspectives. I think it's better maybe to show a picture. That's what I like. Another way to say the same thing, and this is more like the continuous time view. So excuse me, we are in discrete time now, I said, but plots are sometimes nicer with some lines, right? So, and then we talk about subarcs, like parts of trajectories. So any subarc of an optimal trajectory is also optimal. That would be another statement of the same thing. And here again, if there would be another better way from the intermediate state S bar K to the end, if that would be better, then the whole trajectory would already be better by going that way, right? So it's, again, the principle of optimality is quite obvious. If you want to go the fastest way from here to, let's say, Berlin, right? And then on the way, you visit some little town in Germany. Afterwards, you will follow the fastest path from that town to Berlin in order to remain on the fastest path from Freiburg to Berlin, right? So that's another statement of the same principle. And it's all due to the fact that the only coupling between the left and the right arc that you see in the picture is via the state. So if you fix the state for this state, it will be optimal on the left and on the right side. Yeah? So I think it's good to think, to keep in mind that dynamic programming doesn't go in one time direction or the other, but it's a general decomposition principle for problems which are optimization problems which are coupled via, let's say, some well-defined interface, in this case, the state. Yeah? So the state is really defining where the communication between the left and the right arc happens. So this is the principle of optimality, and we can now go into dynamic programming. But before we do that, I want to make a mini prelude, just to simplify the notation. You know, I said constraints are extremely important in MPC and in control engineering in general. So on the left, I have this typical problem that we want to solve in MPC. This is, in this case, already the finite horizon problem with a cost C and a terminal cost that I call big E here. I have the initial value, it's prescribed, then the system dynamics with function F. But we also have these constraints H and R, which actually are path constraints. That's what the H expresses, and R is a terminal constraint, as we say. Just some functions that need to be smaller than 0. And I think a very useful trick for lots of notational simplifications in optimization is to think of optimization problems being able to take in extended real values. Extended real values are not just real numbers, but they comprise plus infinity and sometimes also minus infinity, both, right? And you can actually add a number to plus infinity and it will be plus infinity. That's easy. So most operations are defined in this extended reals. The only operation that isn't really defined is what happens when you add plus infinity and you subtract from it plus infinity. That gives an undefined thing. But very often you don't encounter that, and then it's really useful to think of extended reals. And they allow us in particular to think of constraints as being just regions in state space which have infinite cost. And that's the cleanest way to state a constraint. A penalty is, yeah, you would choose the penalty factor, but then it could still compete with your objective. Infinity will always outweigh your objective, right? And maybe I want to draw one picture here because it's, I mean, maybe I stop the sharing for a moment so that you can see the picture better. And I need to find the blackboard chalk. So I do it like that. So when you have some state space S, right? And you have a function that is maybe your cost function. Could be something like this, nice quadratic. But you also have constraints that say, this is forbidden, and maybe this is forbidden. So you want to be in this interval, for example, right? That could be a constraint. Then this extended value extension basically says everywhere where I'm violating, I have infinite cost, plus infinity here, and plus infinity here. And by this operation, I can still call this would be, so to say, the function C. And then this function here is the function C bar, which has the extended value extension. And one interesting thing why this is really the right way, and there is to represent constraints, it's really fully equivalent to the original constraint problem in the following sense, that the set of the epigraph of the cost function, which is anyway only defined on this set, is anyway given by, let me just maybe make it like this. This is the epigraph, and it will just exactly reproduce the right epigraph for our cost function. Yeah? And typically you choose this definition so that your epigraph is a compact set. Yeah? So it's these numbers that are bigger or equal to the your objective function and that are feasible. Okay, so this epigraph is what we get, so to say, in the extended value extension, and we had it already before if we carefully excluded all points which were not admissible. And so now let me share my screen again. So we could now get away with our constraints. It's nasty for optimization, I should say. Yeah, this is a bit like interior point methods, by the way. They introduced the barrier, right? Yeah, the barrier. By the way, the barrier has some similarity to this. This is the barrier. So the barrier makes it smooth inside, right? And if you make this barrier parameter tau small, then it actually recovers this this extended value extension. So here we just do it for conceptual reasons because I want to get rid of constraints. They will just be tedious and make all my notation clumsy. So I leave them away, and they are not needed in dynamic programming because I'm not relying on differentiability of my functions. That's the beauty, let's say, of dynamic programming. They can be non-smooth functions. So here's the extended value extension in a definition. It's the function C for feasible points. Otherwise, it's infinity. So now I can use that notation. And of course, I don't want to carry this bar all the time. So just have this in mind. And from now on, we just have an unconstrained optimal control problem. But please keep in mind, it could be extended value functions. So it could cover constraints without any conceptual difficulty. So after this preliminary step, now we are now happy that we can formulate our optimal control problem without constraints. And then we can introduce a function that we call the optimal cost to go function. Sometimes it's called the value function. I think sometimes it's in the plus or in the maximizing community, it's the reward to go function, for example. And we define it. And here I somehow mix the S and the X notation for states to our advantage. Let's say S are still the optimization variables, but X is now the initial value of the optimization problem, right? So X appears here. I needed some different names, so I use the X here. So the function j, k of x is defined here at this time point for a given x, is defined as the minimizing cost for the remainder problem that starts at time k. That's the key. So the cost to go is what you would have to pay if you start here, and from then on you behave optimally. So then we can use the principle of optimality on just the interval from k to k minus k plus 1, basically this one step that Bellman spoke about, right? So we say the cost to go at some time step k, yeah, this one, you can, if you would know, and that's of course a big if, right? But if you would know the cost to go at the subsequent time step, and you know, of course, the transition cost, then you could just minimize the sum of the two in order to get the minimum, right? I think we do nothing else when we look for a shortest path, right? Imagine you have now here from Freiburg, yeah? You have two ways to go to Berlin, yeah? You could either go via, let's say, Basel to Berlin, or you can go via Offenburg to Berlin, yeah? They're roughly the same distance, maybe from here. And so the C term would be the same, yeah? But then the cost to go from Basel to Berlin might be larger than the cost to go from Offenburg to Berlin. And that's why we will choose Offenburg, right? So we go to Offenburg because we know it's closer to Berlin than Basel. Extremely simple and extremely useful. So please note that from my optimization perspective, this is a parametric optimization problem depending on the parameter xk, yeah? And it has three variables, the s, little sk, little ak, and little sk plus 1. But these are so trivial to eliminate, in particular the two states. Yeah, this is trivial. And this one we can also just eliminate. So we can write that whole thing shorter, and that's what we typically do. So we simplify this long expression, which I repeat here at the top, by trivial eliminations of the states. We just write it down in the equation here at the bottom. And that is the basic recursion for dynamic programming. So we say the cost to go at a certain state is equal to the minimizing action, the minimal cost that you get by minimizing the combined cost of your stage cost plus the future cost to go of the state where you will end after the next time step. That's a trivial identity. I think it's just true, so to say. Yeah, it is true for optimal policies. That's another statement, so to say, of the principle of optimality. But this can be made into an algorithm if you think of it. Yeah, so the good thing is we know the terminal cost. That's just this function E. So we know that one. So why don't we start there and iterate backward in time to generate our cost to go step by step. And that's the dynamic programming recursion. So you iterate backwards. You start by just defining the terminal cost Jn, the last one, Jn, to be the terminal cost E. You have to basically copy just all the function values for all the states from E to Jn, so to say, right? That's not a long operation. Please keep in mind, and that's maybe already important, you need to know this for all state values, right? So it's easiest to implement it if you have a finite state space. Finite means discrete, combinatorial problems, for example. And hopefully this isn't too big, right? And the first example will have as a state space just the integer numbers. So that could be an easy state space. That would be beautiful. Like that's the dream case for dynamic programming. Yeah? But typically, of course, the state spaces are much larger and sometimes we are continuous and then we would have to discretize. Okay, but then we go backwards. So we let this index k go from n-1 to n-2 and so on until we reach 0. And pictorially, this looks like this. And now, sorry for the x here, it slipped through. Didn't have the energy to change that. Yeah, at 3 o'clock in the morning after having done more important parts of the talk, I decided to keep it that way. So here's the terminal cost. Yeah, think of this as a slice of a cost function, so to say, right? So it's x is the axis that goes into our out of the plane, and you see like an oblique view of our cost function. So think of this as a sheet of paper that you see from so to say this perspective. Yeah. So we have that. We do one step ahead by just going through all states at the n-1 slice. So for each state, we explore what would be the optimal action. And we do this typically, I mean, if the control actions are also discrete, we just try all possible control actions at this state and record where they will lead us. And the best value is what we tabulate then in this field for our state. And then we go to the next state. So you see that each step of this dynamic programming recursion needs to visit, so to say, all states, and it needs to explore for all states, all controls. So it really searches, right? It searches all states and all controls. But the good thing is it does it only for one time piece and not all together. And that avoids another increasing combinatorial explosion that we would otherwise have. So then we continue with this whole thing and we arrive at the end, and then we have J0, and that's defined for all times at the beginning. That's actually not strictly necessary for a deterministic problem where we know the initial value, because we would only, I mean, we are actually only interested in J0 for S0, right? That would be a mini simplification, but it doesn't save us much to save the computation of J0. So we can also just include it. It's just 1/n of the whole cost, right? And it has a conceptual beauty to have it also. So how would we now get the optimal controls? And that's where we enter the notion of Q function. That's something that I think wasn't used by Bellman, as far as I know. I need to look it up. Maybe someone can contradict me or tell me where the Q function originally appeared, right? So it came somewhere. But basically this sum of the stage cost plus the future cost to go is called the Q function in reinforcement learning. And in dynamic programming, I would say as well. So we just call this the Q function. It will be useful later in Q learning in particular. But for us here, it's just an abbreviation of this combination. And so basically, if you define this Q function and then you minimize over all the actions A, and of course, the optimal feedback is then the one that takes the minimizer. So we actually now are able to define our optimal feedback controller, the thing that we were looking at from the beginning, right? So we say pi is this law from states to actions that is defined by the expression here at the bottom, where we say the pi star at time step k for a given state S is given by the argument that minimizes the Q function for that S with respect to A. Yeah, so the control action that actually has the best value. Yeah, so if I go from here to Berlin and I have the choice between Offenburg and Basel, yeah, I compute the Q function for both, which is basically how long it will take me to go to Berlin via Basel and how long via Offenburg. And then the action, either going north or south, that I choose is the one that minimizes this cost, and that is going north. So my action would be going north. So now if I collect all these feedback control laws in one, let's say, sequence, pi 0 to pi n minus 1, then I get a whole policy. That's like a time series. This is only relevant for the time depending case, which we have here. But this is what we call a policy, and this is the optimal feedback control policy. So this will be a complete answer to all our decision problems for this particular problem, because for any time step at any state, it will just tell us what to do. So that would be beautiful to have. And also, if you think of this tabulation that we need for J, we could also use tabulation to do this, right? So basically, if states are discrete and if actions are discrete, then this is just a map from states to actions, which is basically a table. For every state, you could just say, this is the action to take, just stored somewhere. So that's would be useful to have, right? A very, so it's an algorithm that just tells you when you're in Freiburg and you want to go to Berlin, then go north, so to say. But of course, much more. So how would we then get optimal trajectories? So let's look at this original problem again, which I said, which would have an initial value. That's my perspective on this topic. I have an S0 bar. That's where I am now, and I have a time horizon n, and I want to minimize this total cost. So basically, I want to solve this NLP that we see here, number 1. Yeah? I want to solve it with, I mean, it's not an NLP if I have a discrete search space, right? It's agnostic, but it could be also a continuous problem. So if you have this optimal policy, then you can actually just use it to solve the original problem by starting with this initial value and then just simulating the closed loop system, the optimal closed loop system, of course. And so this goes like follows. You start with, we call it S0 star. The optimal first value obviously is the starting value. That's a trivial constraint, but I make a little notational difference here, right? So that's it. And then then I go for the K index in forward time. Now it's forward time, not backward time. Like before we did computations backward. Now we go forward. With this forward recursion, we start with computing what action we should apply for the current state. And then we take that action, plug it into our system model, and simulate to the next state. A simple loop. And then we have solved our optimization problem. And this gives you the optimal trajectories S star and A star, which solve this problem here on the right. So that would be a solution algorithm, and that's how dynamic programming would solve a finite horizon optimal control problem with a fixed initial value. So if you remember, somehow we introduced the notion of MPC a bit sloppy yesterday already in a talk. So I said MPC is just predicting over n steps into the future and then implementing the first control. And that's what MPC is. So actually solving this optimal control problem by dynamic programming delivers you the MPC controller if you like. Yeah? I mean, that would be one way to compute the MPC control law. And yeah, it's maybe interesting to have a mini discussion about that now. So in MPC, we will actually just apply this pi0 all the time, and then we can simulate our system for much longer than just n steps, right? So it's a bit strange. What does MPC do, right? It says, oh, in reality, I want not to solve a finite horizon problem, but an infinite horizon problem. And I just have an infinite policy that consists of pi0, 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 infinitely open. And then I can also simulate my system with this policy. And that's what MPC does. And tomorrow we will discuss the implications on stability of the system and so on that this entails, right? So it's an approximation somehow. The good thing about this is that you actually can compute this. I mean, look at dynamic programming. You just do these recursion, and then you have pi0 for after n iterations, so to say, n steps. And this MPC law you can generate in one of three ways, I would say, and that's actually done in practice. All three ways are taken. I think it's good to keep that in mind. The first one that we just explained here is dynamic programming. So you can use this algorithm, and then you have an explicit notion of what should we do at which state with MPC. The second, and let's say the classical way to obtain it, and that's actually where you solve. Yeah, that's the solve. You solve this problem one online. That's classical way to get this MPC law. And it also gives you this, if you solve it exactly, you get the first control from that optimal trajectory in a different way. So in that sense, B is the normal way that MPC is generating this control law. And interestingly, and that's like, I think, embarrassing if you think twice about it, in the MPC community, yeah, there was a very important wave about explicit MPC. Explicit MPC has some, exploits interesting, very interesting properties, in particular of linear quadratic problems. Yeah? When you have quadratic programs, the solution turns out to be a piecewise linear function of the state and so on. So you can actually pre-compute the problem one for all initial values. It's a bit like dynamic programming, but also not exactly, because you still solve, so to say, a mathematical program, but for all initial values. Yeah? And that is, I don't know how to call it, but it's somehow a mix of the two worlds. I don't know if it's the best of two worlds, right? But it's a mix of the two worlds that, so to say, has to explore the whole state space for all initial values. You have to, so to say, find and you have to solve the problem that you solve online only once. You have to solve it, so to say, for every single state that you could ever encounter. So it's, as Joschka would say, it's so to say, you can later on cash in on this, right? So after you have done this enormous amount of computation offline, the online evaluation might be cheaper. And that's actually one of the reasons why, the only reason I would say why explicit MPC is used, right? That's the only reason, because it delivers the same law, but it might be cheaper. And that's actually what makes it interesting. But what I find embarrassing about the whole thing is that if you are starting to tabulate in state space anyway, I would, so to say, tend to do dynamic programming. Yeah? And that's option A. And yeah, so anyway, it's good to know about all three possibilities, and all three are used. So sometimes people use C, for example. You just run your MPC controller, actually you call it thousands of times, and then you use that to approximate your policy. Yeah. And also I should say that a lot of people in MPC now are looking at how you could, so to say, yeah, synthesize your controllers by just doing this explicit MPC with a deep neural network, for example. But when it really was hot, this explicit MPC field about, yeah, I would say 15 years ago, it was mostly based on the pre-computation of quadratic programs, parametric quadratic programs, which are very efficiently, I mean, not very efficiently, but they are computable offline, because of this property that the feedback control law is piecewise affine. It's basically defined on some critical regions, which are all polyhedra, and so you don't have to tabulate the full space in continuous state space, but you just say, here are the boundaries of some regions, and on each region, the feedback law is beautiful, nice, linear, right? And I just need to store some matrices. Okay, that was a long discussion, but I want to already mention that also Bellman was aware of the main limitation of dynamic programming, and that's what he called the curse of dimensionality. And this slide has a long text. Unfortunately, it's maybe serving a bit as a script, so when you download this slides later. So it's elegant and powerful and can solve every problem. Yeah, could be non-smooth, non-convex, yeah, whatever, to global optimality. Yeah, so it's exploring everything. And I would say it's efficient implementation of exhaustive search. But as we did say already, it requires the tabulation of the cost to go function for all possible states S. And that could really kick it out of competitiveness. And continuous state spaces, for example, if you want to tabulate with, let's say, 100 points in each direction, yeah, 2 times 100 to the power of 2 is 10,000, right? You add 5 dimensions, and then you get 10 to the 10 possible states that you would need to tabulate, and that's already quite a lot. That's only for 5 dimensions, and 5 dimensions is not much for many control problems. It usually requires this discretization of the state space if we do it exactly, and its computation complexity grows exponentially in the state dimension. That's really the problem. And that makes it impossible to apply to any systems with larger state dimensions. So I think maybe if at the end of my life, people might be able to do it, so to say, really exhaustively for 6 dimensions, maybe 7. Yeah? But I'm sure not 20. And not with, without special structure in your systems. And I should say that obviously deep neural networks offer a way to do this approximately, and other approximations as well. So approximate dynamic programming is a different thing, and that could be much more powerful in the long run. And that's actually our interest in dynamic programming now. I said already under option B, classical MPC does circumvent this problem of the curse of dimensionality, so it doesn't suffer from the curse of dimensionality by just doing this restriction on just finding one path. It's just saying, I want to not find all possible paths, but I want to find one path. And typically, I'm even happy if this path is just locally optimal, right? That's the key also. For convex problems, that's the same. So that's why linear programming and quadratic programming are so powerful. And explicit MPC suffers from the same curse of dimensionality, so that's also not curing it. Actually, yesterday we had this quote, which I didn't remember, but that MPC is the poor man's approach to dynamic programming, and actually explicit MPC would then a rich man's approach to it. So to say, if you have lots of computational power offline, you would do it. But then actually you would also, you know, as if you're rich enough, you would also do exact dynamic programming. That's my opinion. Yeah? So there might be circumstances where one is better than the other, but yeah. Dynamic programming has this, I mean, this power that you can treat whatever you like, stochastic systems, robust systems, you don't require continuity and so on. So you have much more freedom once you enter into the state tabulation domain, while explicit MPC is, so to say, restricted by the same restrictions that MPC has, namely linear systems, typically convex cost functions and so on. Okay, actually Katrin and I and some students in the team, Florian Messerer, we had some discussions about how to do a simple example that models the early stage of a pandemic, which is somehow, I mean, now in Germany and most of Europe, we have a slightly different situation because of the mass vaccinations, right? But in the corona pandemic, if you look at like the situation a year ago, nearly no one had it. I mean, at the end, I think only 3 or 5% of our populations had it. So there is nothing related to immunity. And so let's make the simplest possible corona model, which we would agree that it's basically true by making the model simple enough. Yeah. And so the model is written down here at the bottom. So you just say there is the notion of reproduction number, and I assume this reproduction number to be controllable, right? So I can reduce it as a government, we can reduce it, but it will have a very high cost to reduce it because people cannot meet in lecture halls anymore and so on, like we do now. Yeah. And reducing it more and more will make it very, very expensive. Yeah. But this cost, we can reduce it from a positive, bigger than one number to a smaller than one number. And by that, we could contain a pandemic. Yeah, so the minimum R is, in this example, 0.5, which might be true for COVID-19 also. And the R max is 4. Yeah, that's what, when you don't do anything, you don't have costs on social distancing, but you might have lots of cases. So our model is here stated at the bottom. So you just take the product of the reproduction number, which you control, and the infection, the number of infected people in your country. You multiply them, and then you get the next generation of infected people in your country. And we do the floor in order to just restrict all this to integers. The floor also means, which is realistic, right? That if you have quarantined the last person in your country that had the disease, and this person didn't infect anyone, afterwards it's gone, right? So in that sense, this floor is better than the ceiling. I mean, it's more realistic. So you can actually erase a disease in this model. So now, the interest of this model, I mean, the model itself is not debatable, I think. Yeah, so it's a tautology. That's how R is defined. It's the actually that's how we compute R every day. It's like the division of the infectious people, like 4 days ago, with averaged over 4 days, I think, with one period and the next. Yeah, so here we take weeks, but it's not changing the picture. And so now this government is, let's say, really, yeah, relaxed about this disease. So the government says, we put a very, very small penalty on everyone who has it because we know it's a disease. There will be inconveniences and also fatalities. So, but not so many, fortunately. And so for this reason, we penalize it only with a very small penalty. So that's what this government does here. So it has a stage cost that says the following. We have an extremely high cost if we try to drive our reproduction number to the minimum possible, which is only a half. I mean, we will not be able to do it lower. I mean, some governments might be able to bring it even lower, but not here. And there is no terminal cost, so we just have no terminal cost. So I want to illustrate that cost. So the model is repeated here at the top. Extremely simple, as I said, by definition. State space is just the number of infected people. And the cost is growing incredibly when you go to small r. And it's 0 if you have no action. Basically, R max is when you let the disease just spread without any measure, which is also not really realistic because people might stay at home sometimes, right? But let's just assume there's no cost. Everyone would be just happy and relaxed and party, and so nothing happens. Yeah? The economy is just running perfectly. And then there's this little epsilon 10 to the minus 4. We could choose probably even smaller numbers here that is just added to the cost. So we give a very low weight to people that are infected. And obviously it should be proportional because if there are more people infected, you will have more deaths and so on. We will not model here any of these nonlinear effects like saturation of hospitals or whatever, right? So it's a very simple model. Not much to debate about. Maybe this, I mean, everything is nearly tautological apart from the cost of lockdowns. So this might be debatable, how is it? But it should go very high if you're at small reproduction numbers, right? That's what we agree. Actually, this cost will be probably higher in winter than in summer, and these things should maybe make these problems much more interesting. And the effect that we don't model the herd immunity is obviously making this model completely wrong for a later stage of a pandemic, like now, when we have lots of vaccinations, for example. Or if we had lots of cases, then this R is shrinking, so to say, intrinsically. Okay, so this is our model. 2 things, F and C. And now we do dynamic programming, and that's work of Katrin. And I just put the slides here. So in case we have detailed questions, Katrin can also help me to answer them. No, but I think it's self-explanatory. So what we see here on the left for states ranging from 0 to 5,000 people. So we think of a country which has more than 5,000 people. Yeah? Could be Australia, for example, or something like that. So then the cost to go function, J0, I call it J0, but it's actually what we obtain after going n steps backwards. And Katrin obviously didn't compute it for 2, 5, 50, and 100 by starting the recursion again and again, but she just started by going back 2 steps, and then she has J0 for 2 steps, then she goes back 3 more steps, 5 steps, and then she has J0 for 5 steps, right? You go 50 steps back and then 100 steps back. And the interesting thing, and that's also what we see, and that's the first thing I have to ensure that it's true, at 50 and 100 time steps, you get the same plot, right? So they just get identical. That's an usual observation in dynamic programming, and that's actually why MPC works. Yeah? Because if the horizon is long enough, it doesn't matter if you make it longer or shorter. It just needs to be long enough, and then it gives you the right cost to go function, actually the one for the infinite horizon already. Okay, so then this thing at the top is the infinite horizon cost to go, so to say, for 100 periods. You see that the cost to go functions for smaller time steps, like 2, for example, this which is denoted here in red, is much smaller. Yeah, because there, yeah, obviously, if you look only 2 steps into the future, there's nothing spreading, there's no DBZs now, you have 2 people that have it, and there's no cost on it, right? But if you predict 100 time steps, you know there is exponential growth. And then you know, but I can react to it with a lockdown. And so if you look at what this cost to go function is, it's related obviously to the feedback control policy that we have here on the right. So that's the pi0, the one that we would implement in MPC for a horizon of 100 time steps. This is this pi0. What it does is when there are some infected people in your country, you will do a lockdown of a certain form. And it doesn't depend on how many people you have. You just do a certain lockdown, which brings you to a number that's safely under 1, so to bring it down. But because there's this enormous cost growing when you touch to the minimum, you will not exactly go to 1/2, which would be our minimum here, right? But you basically have a very simple policy. If there's no infected person in your country, relax. If there is one, make a strict lockdown. And with this simple policy, we can very easily also explain how this cost to go function comes, actually, because the cost of this fixed lockdown is always constant, right? So it doesn't depend. So while when you have, for example, 4,000 people, what you will just, so how the system will evolve is you will just have decay of your, okay, we didn't model it for 5,000 infected people. That could be another interesting addition, yeah? But if you would start with 4,000 infected people, you would just impose the lockdown, then you would have exponential decay. During this exponential decay, you have this high social cost for the whole society. Everyone has to do this lockdown, right? And after then the exponential decay is over, you have eradicated the disease and you relax. Yeah? So basically, this is an exponential function where the y-axis is, so to say, the input of the exponential, and then the I is the exponential. That's what we get here, yeah? Because of it's basically reverse time exponential decrease with a constant cost. So that's what we see here. Maybe interesting is that it's extremely steep at the low end of infections. Yeah? So that's actually what makes it favor to do this harsh lockdown at 2 or 3 people. That's actually what Australia does, right? So what we found interesting is what the early stage pandemic would do if you would have a shorter prediction horizon in MPC. And I think a short prediction horizon is not a bad thing in life, right? I mean, that's most of our decisions are based on a short prediction horizon. And yeah, if you drive a car, sometimes actually you cannot predict the whole trajectory, right? So what we, in German, we call this auf Sicht fahren, yeah? So you do just a short prediction because you don't know the future so well. I mean, you don't know even if your model is true in the future. But what happens now if you run, so to say, a short horizon MPC for the corona or for the early pandemic phase? And what's interesting about that is if you have this short horizon of n equals 2, which is, maybe let me show the policy. It's this policy that we show here in red. So yeah, you relax if there are few infections, and you start to lock down more and more if there are more, right? Because you have a prediction horizon of only 2, you you remain pretty relaxed, and you are nearly actually at 1 all the time. But you will actually not have an explosion. That's a good thing. So even that one is controlling your system, right? So stabilizing your system. So with a short prediction horizon, you would just say, hey, at some point, your optimal feedback law will actually tell you, no, you should actually reduce, because otherwise we get this enormous number of infected people. So the epsilon penalty kicks in, so to say. But you will actually stabilize on a steady state that's pretty high. Yeah? If you have this short-sighted horizon, and if you have the long horizon, which is basically like infinite horizon, then what you get here in the same scenario is basically you stay at 0 all the time. And, next time we do this, I think we should also simulate starting. What happens if you start with 4,000 people imported? I mean, that's basically how China started at some point, right? Well, we'll just go down. So it's easy to predict. Here, Katrin actually added disturbances, like imported cases from another country. You know, Australia lets in, I think, like 3,000 people a day or something, or a week, I forgot. And some of them might bring in the disease. Okay, so this is the early stage of a pandemic. I found that interesting, because the model is relatively simple and not so much debatable, and the cost of infected people is relatively low, and you can de-emphasize it. But if you take this model serious, and you also only think of the early stage of a pandemic, that it seems to be really optimal to just shut down quickly. So in some sense, we can be quite proud on most of the world's governments, what they did, right? So they behaved somehow, actually, it's a question. I mean, in Germany, we are more to the 4,000 steady state. At the moment, we have 1,400 steady, not steady state, even growing a bit. So it might be a bit short-sighted, what we do here. But some governments really had this complete optimal policy implemented. I think this is a good moment to start the discussion. So we stop the recording, and so now we explain like the prototypical case where dynamic programming actually leads to a nice and beautiful computable solution, even in continuous state dimensions of non-trivial size. Yeah? And these are linear quadratic problems. So I want to look at this type of problem where you want to minimize a state and control trajectory. Sorry for calling it X and U now. Yeah? Where we have a quadratic cost, just quadratic deviations from 0 are penalized. Also, we have a terminal cost that I call already Pn here. Then I have my linear system dynamics, a discrete time linear system at the bottom, and an initial value constraint. Maybe one little difference to what we did before is I added a time index here. I mean, this time index can be easily added in finite time horizon MPC problems. So the dynamic programming isn't affected. I mean, it's just easy to carry all this over with a varying index, and things might at some point be time varying, and that's why I like to add it here. And if you look at that, from yesterday's perspective of optimization, this is a finite dimensional quadratic optimization problem with equality constraints. And you remember a linear system solve, and you have solved it. So in principle, this is not a problem. Yeah? So you could solve it. But we could also apply dynamic programming here, and it's an exercise for our mind, and it will lead to an interesting algorithm to solve the linear algebra problem, actually. So that's what we do. So how do we apply dynamic programming here? And so first we need to somehow collect terms, right? So if the stage cost is just given by this quadratic expression, where, by the way, these matrices are usually assumed to be positive, definite, or semi-definite, this whole matrix here. We have our terminal cost at jk plus 1, we represent by some matrix P. So we have a quadratic terminal cost and a quadratic stage cost, and we have a linear system, then the dynamic programming recursion that we remember, right? It's this minimization of the sum of stage cost plus terminal cost. This gets actually also a quadratic expression in x and u. So that's this Q function actually. Here is the Q function, right? The Q function is quadratic in x and u. So now one interesting and easy thing, I think it's extremely simple to know this conceptually. So if you have a convex quadratic cost function in x and u, then this is a parabola in x and u. In two spaces, x and u. But then we want to minimize it over u. So you have this paraboloid, right? You want to minimize it over one of the two dimensions. That means actually projecting it into the x space alone. It's like watching this epigraph of the cost to go from the perspective where you don't see the control actions. And then you see the minimizing function. And that's actually the cost to go. Obviously, if you take a paraboloid, you look at it from one side, it will be another paraboloid, right? And that's the key to linear quadratic control. So this minimization that we see here, which is minimization of a quadratic function, is another quadratic function. And that's basically already the essence of what follows. So don't get lost in the algebra. So we simplify notation a little bit, and we state a lemma that is commonly known as the Schur complement lemma. So if you have any quadratic function that I call phi here, psi is the original function in two variables, the one that we can look at. And if you project that onto one of the dimensions, that's basically what minimization does, then you get the function phi x. And so the function phi x can explicitly be computed from your matrices by what is called the Schur complement of Q with respect to in this matrix here, and that is Q minus S transpose times R to the -1 times S. Yeah? You can always compute that if R is invertible, and actually in our case it makes only sense if R is positive definite, because only then this minimizer is defined. And then you have this function phi. And also the minimizer itself is given by this little expression here at the bottom. So you have two little linear algebra operations. We don't prove that here, but it's just basically reflecting the fact that a quadratic function, if you minimize it, the minimizer is a linear function of the x. The minimizer u star, so to say, is the function of x. And the minimal value is another quadratic. So these two things are just the only things we know. And now let's expand that QSR matrix already to this long, clumsy thing that we had before, right? Because that's what we need to minimize. So I go back one slide. So this at the bottom is what I want to minimize. So let's just take this Q and R to make them more complicated. And then we have this expression here. And what needs to be invertible is now this expression here on this side, here this, right? And then you can directly compute the new cost to go, JK, with a matrix that I call P new, the new matrix here, which you get from a slightly lengthy expression. I don't want to go into detail, but it's basically this cost of Q that I had anyway, the next stage cost, and then here this negative part, which is taking into account, so to say, that we can control. So the beauty of this is if you start with a convex cost to go, you have a linear system, you have a, with a convex quadratic cost to go, you have a linear system, a linear quadratic cost, then you're after one step of dynamic programming, you again have a convex quadratic function. And so then you can go on. And then you just go on the whole functions, and you could do following difference Riccati recursion. Obviously, you start at the end. You take this matrix Pn, which was our terminal cost as initialization. Then you iterate with that backwards, so that you give now an index Pk. And Pk is implicitly computed from Pk plus 1. So all the other quantities are quantities that we knew before in the statement of the problem, right? Time index cost matrices and system matrices. And after you have computed all these P's, you know the optimal feedback laws, and these are actually also by the Schur complement lemma, and you get them by these matrices big K with little index K. So sorry for the double usage of K, but I mean, one is big, the other is small. And these optimal feedback laws then basically allow you to solve the whole problem by the forward sweep that we remember. The forward sweep is now going, you start at the initial value, and then you plug in your states, you get your controls, you take the controls and simulate your system forward. And after a forward sweep, you will have solved your whole optimal control problem. So as I said, this is nothing else than a solution of a linear system. And in order to somehow make the relation clean, I should say that one can also obtain multipliers. Yeah, I call these multipliers lambda star of index k. They are just the product of p times xk. Yeah? Maybe for experts, it's actually the gradient of the cost to go function, what these multipliers mean. Yeah? But so if you have these multipliers, then the triple that you get from x star, u star, and lambda star, all these things together, they satisfy, you can show they satisfy the KKT conditions of this original optimal control problem, if you would think of that as an optimization problem. So I don't write this down here, it's lengthy, but it's basically satisfying the linear system that we would need to solve in order to solve the original problem as a bilinear algebra. And so from that perspective, and that's, I think, an important point of view, you could say this Riccati recursion is nothing else than just a structure exploiting linear algebra routine. Yeah? So that's, I think, the view that we should take on the Riccati recursion. So it does so by first doing a backwards matrix recursion and then a forwards vector recursion. Yeah? So that's what it does. I should say that in reality, things are more complicated. So the time index was already one complication. I could add extra gradient components. I could add extra offsets to my linear systems. I call these inhomogeneous linear systems. They don't change much, right? But now your formulas that we just stated and which were already long enough, they get even longer and more clumsy. Yeah? And I want to give you a very simple way to remember these long and extremely clumsy formulas that we would get in this case. Yeah? Here we have actually a general quadratic cost with gradients. And maybe it's a bit unusual to have this statement, but it's really useful to think of this one here in these matrices because it makes your whole problem statement fit in one line. Yeah. Otherwise, my cost function would already be too long to write it down here. But it's not only that, it's also actually at the base of the trick that I want to share with you. But let me first motivate why you would need that. So why do you need inhomogeneous systems and costs? Because first of all, they come as linearizations of nonlinear systems. And we will see that's actually what's done also in ILQR, for example. But also in many other nonlinear MPC algorithms. Then if you have reference tracking problems, you will have these inhomogeneities. Also, when you have filtering problems like moving horizon estimation, you will have inhomogeneities. And also, if you have subproblems in active set methods or in interior point solvers, so if you have inequalities, at some part, you will have to solve linear quadratic problems with equalities only, and then you might also have time varying indices. So, sorry, not time varying, but these extra gradient terms. So, with a simple programming trick, you can actually use the recursions that we just had before in order to do the computations. And this trick is maybe not how you would implement it, but this is, I think, a good way to remember it. So you just say my system state will be augmented by a state that has basically the meaning of one. It is a state. So it's actually really an optimization variable from this perspective. But it's always one because I started one and my dynamics preserves it to be constant. So it will remain at one. So I replace the dynamics by this formula in the middle. I add this extra row and column to my state transition matrix. And then I also have this initial value. And then I have transformed my problem from before into a homogeneous problem, and I can just state it as it was before and apply the algorithm as before. But now all my matrices have an extra row and extra column. So nothing spectacular, just something to remember. And now is a good time to go to infinite time horizon problems. Maybe after short moment of discussion, maybe I will not stop the video. I will just admit 1 or 2 questions that we can read. If you have a question. Yeah, there is a question in the room.
So I guess this recursive recursions is what HPIPM uses for the OCP.
Yes, so the question was about the QP solver HPIPM, which is an interior point method for MPC problems with inequalities. And in fact, it uses a Riccati recursion inside the linear algebra. And that's what makes it efficient. And actually, there's many other tricks inside that solver. So it's surprisingly fast. Okay, maybe that's it for the questions now, because LQR is relatively easy compared to the rest, I would say. Let's now go to infinite horizon problems. So now, as we already had discussed, we would like to not have a terminal cost, and we just would like to look infinitely long into the future. And that's basically meaning that we have now, again, an infinite search space, right? Infinite long trajectories. And we just add this infinity symbol here and here. That would be a problem that we want to solve. And the interesting and beautiful thing about dynamic programming is that if we make this assumption that a steady state can be reached of this dynamic programming recursion, so if the J's, in fact, like we have seen at this Corona example, right, at some point this cost to go function will become similar to the previous one. So if you just impose that as a condition, then you get what we call the stationary Bellman equation. So that's a functional equation on J, and J is not having an index now. So it just says 1J should be equal to the J after 1 step of dynamic programming. So the J shouldn't change under dynamic programming. And that you can, so to say, state as an equation. And then you just have one function J, and that is the answer to all our problems, right? Because if you would know this J, then it gives you the term, the cost to go for infinite times, yeah? And if you compute the Q function related to that, then this gives you an easy means to get the feedback law. And this pi star also doesn't have a time index now. And it's the optimal feedback control for infinite horizon problems. And it's, I would say, the holy grail of this course, right? That's what we would want to have all the time. Everything else is an approximation. This can be sometimes computed. But sometimes it's actually ill-defined, in particular when your costs are not going to zero. I mean, if you have a state, a safe state where you can stay at zero cost, like, for example, no infections in your country, right? Nothing. This would be the cost state with cost zero, then this will work, right? It's the shortest path problem, you could say. But if not, if you have a running cost that is persisting, like most things in life, then this whole thing might not lead to a well-defined solution. And then there's a trick that's actually also done by economists and which somehow reflects reality, is that you say what happens in the future doesn't concern me as much as what happens now. And you discount future cash flows or duties or so on, right? So you have this gamma, and we call it gamma in this course, the discounting factor, which is typically between 0 and 1. And then you just multiply future costs with something that's getting smaller and smaller. Yeah? Gamma to the power of I is very small. And the interesting thing is, because of this exponential weighting, this immediately leads to a minor modification only of the Bellman equation. You just multiply the future 1 step ahead, cost to go with 1 gamma. And that will automatically give you the perfect solution for the infinite time problem with this discount. So this discounting makes persistent costs not lead to infinity. So if your minimal cost that you could anyway achieve is 1, then this gamma series adds to 1 over 1 minus gamma. Maybe you remember, right? So it's a finite number. Okay, so the stationary Bellman equation can be saved in this case, no problem. And another interesting thing in this context is that you could also think of linear quadratic problems. Now I dropped the time index again, so there is Q, S, and R without any index, yeah, because if you go to infinity, you shouldn't have time invariant problems here. Also, the A and B metrics are constant here. I think here should be a minus sign, sorry. And we could also apply dynamic programming here. How would we do it? We would just say we require a stationary solution of the Riccati recursion. So we say P equals P. And this leads to an equation that has the P nu and the P that enters equal. And that is called the algebraic Riccati equation in discrete time. And if you have solved that, and there exist dedicated solvers for that, in MATLAB, for example, you get the optimal feedback control for linear quadratic problems explicitly, and you just have one matrix K, and that's the beauty now of LQR, and that's actually why LQR is used. So you have this one matrix, and that matrix you multiply with the state, so your feedback law is just A equals minus K times X, S. And on your embedded system or wherever, you just implement this matrix vector multiplication, and you get the perfect, wonderful, infinite time horizon feedback law for linear quadratic problems. Yeah? So that's why LQR is popular, because first of all, linearizations are good approximations of reality in the vicinity of set points, and very often this gives an extremely reliable and easy to implement solution. And I should say, as an extra note, is the cost for the optimal trajectory that starts at any point as 0 is then also given by this P. So somehow the output of LQR, when you call it with MATLAB or with other tools, is a matrix P and a matrix K. Matrix K is really what you need to decide on your actions. It's the feedback law. The matrix P might help you at some points, and this is important for MPC. Very often we use this P for terminal cost, yeah, as an approximation of terminal costs, even in the presence of constraints. So this P matrix can be useful. So here's an infinite horizon problem that we call the Winterhell example. It's something that is a bit inspired from an idea that Jim Rawlings brought up during a PhD defense, and which sometimes happens in his previous home, which is the state of Wisconsin, which has very harsh winters, very cold winters. And sometimes the roads are so icy that the friction of the road isn't enough to actually make it possible that you can stand still on the slope of your road. Yeah? So you would just slip down due to gravity. So obviously you can still go up a hill. And how do you go up a hill? And that there are some hills, like you have a flat road, and then there's a little steep slope, and at the end you are a bit higher, and that's where you want to be, on a plane that's a bit higher. The desired endpoint is here on the at the point 0, 0. Your position is here, and the height is 0 at that point, but it's actually a bit going down at point -5. You have a very steep slope, and here's the problem. As a dynamic system, you could express it like we do here. We have a cost that just is quadratic, nice, quadratic convex. We just say we want to be at the 0 location, and our control, and that which is actually the force with which our tires can, so to say, push against the ground in the forward direction or backward direction, is limited by something that's 1.5. And note that this is smaller than this 2 that we have here. So that's why we would slip down. Yeah, and people in that state, they know, okay, you have to, I mean, first of all, if someone is before you who seems not to be very experienced, it's better to keep a distance. Do you know why? Because if you drive behind that person, that at some point he might just slip into you, right? So you better keep a distance. And then the second thing is, after the slope is clean, you might even go back, and then you accelerate a bit, and then you go with some. And that's actually how people drive in that state. So let's just compute the cost to go here. Here, k equals 50 was already enough. I mean, I think we should call it n. Yeah? So it's actually like more or less the the infinite horizon cost. And the LQR cost is also plotted here. The LQR cost is 0 at 0 here, and then it's growing, and you don't see so much here. The nonlinearity of the system really leads to a significantly different exact dp cost here. And that's actually this interesting thing is low cost is yellow and high cost is black here, or purple. But here's this interesting discontinuity in the cost to go. So that's exactly the decision line when you are, for example, here at with 0 speed. X2 is the speed at a location which is a bit already above on the good side of the hill, so to say, on the higher side. Then you will at some point be able to just drive straight to up there. That's this big yellow region. But then if you're a little bit behind, and in particular when you're at location -5 with no speed, right? At this nasty point, at that moment, what will you do? You will just let yourself slide down, maybe even accelerate in reverse direction. So you drive actively backwards in order to gain some distance soon, and then be able to quickly accelerate back and then go up the hill. So that's this discontinuity here. This discontinuity is also plotted here. I like the plot in the middle. So here's at what's the cost at if you start with 0 speed at certain locations. And so, as we said before, if you start like slightly on the good side, which is between -5 and 0, then you're fine. But if you're coming too close to this problematic point, -5, at some point your optimal strategy is to slide back and then forth, and that's why the cost is definitely much higher there. And if you have a higher positive speed, then your cost is obviously a bit lower because you have already this positive speed, and you might, for example, at the point 5, you might still be able to go up. It takes, here it's really crucial, it's nearly at the boundary of still being possible. If you have a negative speed, obviously at -5, you have to go back. Okay, I think there are more plots for this example. So this is the state to control map, the thing that is, so to say, implementable. LQR is a linear feedback controller. So you see this also here in this context. So it's basically steep linear function. I think in this case, we clipped LQR. Yeah? So LQR is clipped here to -1 and +1. That's why it's not linear. It's actually chick, chick, chick. Yeah? It's a practical LQR. So that's why it has basically 2 regions, one with positive acceleration and one with negative acceleration. It's completely wrong when you're in the steep nonlinear region of your system, where it would be better actually to decelerate in some region. That's this red here. So you go reverse. Okay, let's not discuss it in too much detail, but maybe some interesting results are here. Closed loop trajectories. Left is when you are already on the good side. You start nicely. You have enough speed. You're safe. So you start at position -1 with no speed. And then your LQR will lead you to the point and not be very different to your optimal feedback control. But once you're here at no speed at -5, then the dynamic programming solution will guide you back. Also, an optimal control problem that you might solve could guide you back. But LQR will miserably fail. Yeah, it will just, I mean, you would just try to drive up this slope again and again and again with your stupid controller. No, actually, in this case, it would just have the, not even again, it would just try to accelerate uphill. And because your slope is there, you would actually, this will lead to going, I mean, you drive up and then you will oscillate back, but you're still trying to go there. So you drive at, once you are in the flat region, you drive, you get enough friction again to accelerate forward, but then, okay. So you just oscillate on the slope. That's like what a very inexperienced driver might actually start to do. So yeah, also this, thanks to Katrin. Very nice visualizations. And the last 2 topics are relatively short. So I think we might do them now. Are you ready? Good. They are short because they are so easy. So the funny thing is, if you have a stochastic system, sounds like a really complicated stuff, right? But for dynamic programming, the solution is as easy as this slide. So if you have a stochastic disturbance epsilon that might affect your system F, but it could also affect your cost. So you don't know the cost, it's just stochastic. Then you could just add this little expectation operator on your cost to go, and that already solves the perfect closed loop planning problem for stochastic systems. So you just need to add an expectation operation before you minimize over A. So we take first the decision on A, afterwards there's some random realization of noise that we don't know yet, but by taking this expected value, we can define our Q function. Q is now the expected value. So that could be exactly done by integration here. I mean, that's how you would mathematically define it. In practice, you might actually just sample it. And then it could be a weighted sum of all the samples that you realized. So this is, of course, more expensive than deterministic DP because you have still to formulate to compute this average. But on the other hand, it's just another loop. Yeah. So if you have 100 realizations of your uncertainty, you just have to do 100 more iterations, but it's not any exponential growth or something, which you would get in what we call scenario trees, which would be, let's say, the MPC approach to stochastic problems. So that's, for me, one of the major reasons to think of dynamic programming as really interesting. It's because you can address stochastic problems that you could not address with deterministic MPC. The other thing is robust dynamic programming. And that's less treated in most textbooks, but it's, I mean, it's in principle, it's also at the back of the basis of games, right? So here you're what we had before is an expectation. So now I call the W, the variable W that we don't know, but actually it's not unknown, but it's just chosen by an adverse player. So you would say there is not an expectation over W, but it's someone else who chooses it in order to damage us. Yeah? And I call it robust because it's exactly the assumption that people take in the robust control literature. The robust control view is, I want to have a controller that is robust against all disturbances in a certain set. Yeah, everything should be covered there. And so here you just have this max operation, and then you get robust dynamic programming. So if you have, let's say, if the adverse player has 10 actions against us, then you need to add this extra loop of exploring all 10 possible actions that the adverse player can do against us. So just complexity of everything increases by a factor of 10. That's it. Not anything exponential again. Okay. And there are two properties of dynamic programming which are theoretically interesting and important. First one is monotonicity. And I think it's also good, this slide is also important because it introduces an operator that I call T, which is called the dynamic programming operator. So I define it by actually the action that dynamic programming does on one cost to go. So if you have a cost to go function at one time step and you want to compute the one at the previous time step, then the action that does it, you call this the dynamic programming operation. So it's basically something that takes a function in and spits another function out, which corresponds to the dynamic programming cost to go one time step earlier, right? So this is an operation in function space, so to say. And now compactly, we could write this Bellman recursion, right, as just jk is equal to t of jk plus 1. That's, so to say, what it is. And then also in this function spaces of j's, we can define a half order. So we write actually that one function is bigger than another function if at every single state it is higher. Yeah? So one cost to go could be higher than another one if it's everywhere bigger. And then, because if something is everywhere bigger, any optimization will not make it smaller than than the other, this monotonicity is actually preserved. So if you have some function which is bigger than another, then this will lead that T of j is also bigger than T of j prime. So that's what we call monotonicity in dynamic programming. And interestingly, this also holds for robust or stochastic dynamic programming. So it's very easy to show. It's always holding. And you can use that, for example, for existence proofs or for solutions of the stationary Bellman equation. Yeah? One thing is if you have positive cost and you start with 0 cost, after one time step, you will have increased it. So you know that when you continue dynamic programming, you will just increase. So you have a monotonicity there. In MPC, we try to get something even more nicer. We want to have the terminal cost be bigger than the cost to go after one time step. So yeah, we actually want to be a control Lyapunov function, as we call it. And we will cover that tomorrow. And then interestingly, that implies that our cost to go, the one that is relevant for the MPC controller, is also having this Lyapunov descent property. And that's actually already in one line, so to say, the basis of MPC stability proofs, which we will discuss in more detail tomorrow. So monotonicity is interesting. But there's another property which is not as general, but it holds for linear systems. And so sometimes actually this operator T preserves convexity of the value function. And I think that's also important to understand, for example, explicit MPC, yeah? And things where you have convex cost linear systems. And so if you have a affine system, which might still depend on some uncertainty W, which could be either robust or stochastic, right? But it can depend in any arbitrary way on it, but it should be linear in S and linear in A. And the stage cost should be convex in S and A, in states and actions. Then there's this similar to monotonicity, so to say, if you take a convex function in, you do that one step of dynamic programming, you get another convex function. And I will omit the proof of that. I mean, it's on the next slide. But that could be useful for 2 reasons, or 3. So first of all, if you know it's convex, yeah, then maybe if you're in continuous spaces, now you could actually somehow do this minimization of the Q function actually with a derivative-based solver. That's of course only true if you represented everything with convex functions. And that's the other interesting thing is convex functions can in theory be represented by the intersection of lots of, the maximum of lots of linear functions. Yeah, so that's what we have here. So you could just have lots of linear functions. And together they, so to say, represent any convex function. Yeah? But that could be a very different representation than tabulation in state space. Sometimes much more efficient. And in robust dynamic programming, there is another advantage of this. So in a special case, which we call polytopic uncertainty. So if your uncertainty enters linearly into the system as well, I mean, not additive, multiplicative linear, but linear in W. And this uncertain parameter lives in a polytope. Then because of this convexity, you know, the worst case is always taken in one of the vertices of the polytope. And that makes it, again, possible to approximate, to do exact dynamic programming with finite enumerations. So sometimes, let's say the worst case is always at the boundaries, and that's very beautiful. So in that sense, sometimes this convexity is good to know about, and I think it's also important for intuitive reasons. So if you think of linear MPC, what it generates is actually, so to say, a convex cost-to-go function with a piecewise linear controller. So now we are ready to summarize. So please remember the dynamic programming recursion, which takes one cost-to-go function at k plus 1, creates from it one at k. We get the feedback by minimizing over this function, which we call also the Q function, Q being the cost, stage cost, and the other. You can analytically solve these linear quadratic problems, and you get just a feedback which is linear matrix vector multiplication, so extremely cheap to implement online, so that's really useful. In contrast to online MPC, dynamic programming suffers from this curse of dimensionality. That's like the main bad point to remember about it. Also, in contrast to online MPC, DP can easily address stochastic and robust problems. And from my perspective, that's the main advantage of it. So this is what I think we should all remember about dynamic programming. And as I said already at the beginning, I really recommend the textbooks by Dimitri Bertzikas, who really help to present all these concepts in an extremely clean and nicely explained way. Thank you very much.